Right, let's continue. Do we have any martial artists here who can do some like kung fu jump in the air? I could do it in the past, but now I'll probably like break my hip or something. So I don't have the dexterity or flexibility to do that. But like, could someone do something like this? Like, look at that. Yeah. All right. So that's pretty cool. Right. So we kicked error analysis out of the way. And error analysis was not even a chapter. It was just, hey, getting introduced to the world of numerical methods. We deal with errors, learn about Python. Today, we are actually starting on numerical methods and actually solving realistic problems with numerical methods. So we defeated errors. Next, it was you guys versus Python. So if that's Python on the right and you're in, what is it from Kill Bill? That's the costume, right? You've seen that. And so if like this is Python and that's you, right? So look at that, right? So you ripped Python apart, right? Okay, so that's you. Next, we're gonna go after algebraic equations. I know it's cheesy, like I love martial arts a lot, and so all movies with martial arts is like, like if you want to distract me in an exam, just like play a Bruce Lee movie or something, or Jackie Chan, I'll be distracted. So that's always a winner for me. Okay. Unit 1 in the grand scheme of numerical methods, I think if you remember or not, from the beginning I said there's 3 big themes that I want to talk about and teach you about in this course: solving algebraic equations, dealing with data, and solving differential equations. Right? We will start today on our first unit, solving algebraic equations. And in this unit, we will learn to deal with 2 types of algebraic equations, what we call linear equations, where the variables show up linearly, whatever that means, and nonlinear algebraic equations, where the variables show up nonlinearly. You have sines and cosines, cosine u solved for u. Right? So it's a nonlinear equation. Okay? But all of these equations are algebraic. There's no derivatives in them compared to doing differential equations, which we'll do at the end of the course, where you have equations with derivatives in them. So this first unit will focus on algebraic equations. And the first part of this unit is going to be focused on linear equations, which I will call linear solvers. So these are methods to solve linear equations. With nonlinear equations, we're going to call them nonlinear solvers, obviously. Okay, so we'll start with linear solvers. And as usual, if I find the microphone, I will show you a film. It's a very long film, so I'm gonna chop it probably after a minute. All right, let's see. Oh, nice. Okay. All right. Oh, sorry. Okay.
This video provides an overview of an analysis conducted by the National Institute of Standards and Technology, or NIST, to provide insight into the dynamics of a fire that resulted in the injury of 7 Prince George's County firefighters. On February 24th, 2012, a wind-driven fire in a condemned single-family residential structure resulted in the serious injury of an officer and forcible entry firefighter from Truck 809 of the Prince George's County Fire Emergency Medical Services Department. Examine the fire dynamics of this incident at the request of the department. At 9:11 in the evening, a call was dispatched for a residential structure fire in Riverdale Heights. Truck 809 was the first due truck and arrived on scene within 3 minutes of the dispatch. The 809 officer observed smoke moving extremely fast through the front yard and across the street. The Truck 809 officer and forcible entry firefighter proceeded directly from the truck to the front door of the structure. Less than 1 minute after the arrival of Truck 809, officer and forcible entry firefighter, both in full PPE and SCBA, have entered the structure and began their primary search of the first floor. Smoke and heat conditions on the first floor worsened, and the front door slammed shut, trapping the two members of Truck 809. Within 30 seconds of the door closing, the Truck 809 officer cleared a portion of the living room window on the front of the structure and exited to the outside. Truck 809 forcible entry was unable to self-evacuate and continued to endure the elevated thermal conditions in the living room. Although Truck 809 officer had sustained injuries and damage to his SCBA, he alerted other firefighters that his crew member was still inside. Fire attack had started from the basement door on the rear of the structure. The front door was reopened, and a group of firefighters, including the Truck 809 officer, entered the living room, found the downed firefighter, and pulled him outside through the front door.
In February of 2012, I had a fire on 57th Avenue in the Riverdale Heights community. It's a single-family house, just like any other small single-family home in the county. First arriving units reported smoke and fire showing from a basement level. It's about 9 p.m. It was a red flag day, meaning the Weather Service had instituted a red flag warning for high winds and dry conditions. The truck and the engine arrived together. Truck crew of 2 for the inside crew went ahead of the engine line. They were going to initiate a search for what appeared to be an occupied home. They made it in a front door that had a swing opposite what you would consider. So instead of swinging to a wall, the swing was into the middle of a room. Fire was in a basement below. When they entered, the hose line had not made it in the door, and the energy from the flow path that was now created coming up from the basement steps and now out the front door that they had just opened, that energy slammed that front door shut behind them. Within a matter of 2 minutes, those first 2 firefighters became trapped, and one of them incapacitated. The one smaller of the 2 was able to bust out one window, which was not big enough for him. Of course, that created another flow path. He got to a bigger window, bust that out, created a bigger flow path, but he was able to get out. He was then able to get the engine crew, who was still on the front porch, had not made entry yet. He was able to get them to help him force open the front door and pull the other young man out. That young man was in a burn center for 45 days, nearly lost his life.
NIST's Fire Dynamic Simulator, or FDS, was used to provide insight into the dynamics of this structure fire. The results of an FDS simulation are visualized with another NIST program called SmokeView. The inputs and details for the FDS simulations are documented in NIST Technical Note 1870. The fire started in the basement near the windows on the rear of the structure. Based on an assessment of the fuel load in the burned area of the basement, the estimated peak heat release rate of the furnishings and interior finish was approximately 9 megawatts. However, the lack of oxygen limited the fire growth until the front door was opened. As seen in the heat release rate graph, after the door was opened and allowed additional oxygen to enter and mix with hot fuel gases in the basement, the fire heat release rate increased, with some of the burning occurring on the first floor. Comparison of the simulated initial fire conditions in FDS versus the post-fire damage of the exterior of the basement corner, where the fire started. The wind was blowing from the rear of the house to the front. In the model, a steady wind speed of 20 miles per hour was used. The output from the FDS simulation can be used to provide insight to the flow path within the 2-level structure. Fire gases move from regions of higher pressure to regions of lower pressure. Notice on the outside of the structure that the upwind side of the house, or the rear of the house, is under a higher pressure than the downwind side, or the front of the house. The inside of the house has been pressurized by the wind from the openings on the rear side and the pressure from the fire gases. Once the front door is open, the high pressure on the rear of the outside of the house and the inside of the house equalize. One of the hazards to firefighters located in the exhaust portion of the flow path is convective heat transfer from the fire gases. Convective heat transfer depends on the velocity, the amount of turbulence, and the temperature of the fire gases. This video shows the change in gas velocity on the first floor after the front door was opened. Notice notice the distinct flow of hot gases from the doorway at the top of the basement stairs to the front door. An arrow shows how the hot gases traveling at 10 to 20 miles per hour would have impacted the front door and forced a close behind the truck 809 crew. This video shows the calculated change in gas temperatures as a result of opening the front door, which increased the flow and mixing of the fine gases within the house.
That's why the door should open towards the wall.
Generate hazardous thermal conditions within a flow path. Stay upwind of the fire. Uncoordinated ventilation or uncontrolled doors can also be the cause of increased thermal hazards within a flow path. When sizing up a structure fire, choose your tactics with potential flow paths in mind. Recall that
Right. The video is long. You can watch it. The link is on the slides. But I just wanted to show you that those temperature and velocity profiles. So that's the kind of research I do in my group. This is a technique called computational fluid dynamics. And it starts with numerical methods. I want to tie this to linear systems. So the previous video uses a technique called computational fluid dynamics. And that technique solves the equations for flow, water flow, any liquid flow. Okay, they're very complex differential equations, but we understand how to solve them, and it can also analyze heat transfer and energy transport. Okay, now the numerical solution of these equations usually results in very, 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 very large systems of equations. Okay, and so let me explain how this works. So this is just a rough idea of how this would work. So you would so how did they do this in FDS, that software? They would take the entire problem domain. So in this case, I'm just showing a slice in 2 dimensions. And they would chop it off into small regions. Okay, so this is called a grid. Okay, we will learn about that later. And then at each one of these little rectangles here, or squares, they assign a variable for temperature, velocity, pressure, density, whatever you're tracking. Okay, smoke, etc. Okay, and then we take the full differential equations and do some magic with Taylor series, which we will learn at the end of the semester, and convert those differential equations into systems of linear equations. It's very powerful because we don't know how to solve the differential equations analytically. You cannot solve them numerically without doing any of these Taylor series stuff. So what ends up happening, you get like a little equation like this at each one of those points, which connects the variable at that point to all the variables at the other points. So those become your unknowns. When you solve them all together, you can find the solution for this problem. You solve them all together and you march in time. So you start from 9 o'clock and then you go all the way to 9:30. And in each one of those steps as you go along, you have to solve the same system of equations over and over and over again. Okay? So this is very relevant. And in this chapter, I will teach you about this. We will actually solve a heat transfer problem in 1 dimension that has these equations in it. And we'll see how we can build a linear system of equations from those. Okay? I'll cover the learning objectives and a little bit from the beginning, and then I'll let you go. So I'm hoping at the end, my goal at the end of this chapter is that you should be able to define a linear equation as compared to a nonlinear equation. I know it's kind of, you see an equation, you're like, it's sort of obvious that it's linear or not, but still it can be challenging because it depends on what you call your unknowns and what are your known values. Distinguish between linear and nonlinear equations, identify a linear system of equations, and if I give you a system of linear equations, write it in matrix form. Why matrix form? Because it's beautiful, and it also formalizes our communication about systems of equations. And I will teach you that every time you see a matrix, you immediately connect that to a system of linear equations, because a matrix always represents a system of linear equations. What it's solving, it's a different discussion, but then you take that matrix and make arguments and do reasoning on the matrix alone without thinking of the linear system. That's the power of that kind of stuff. Identify rows and columns in a matrix. So if I tell you what is coefficient A 5, 4 in the matrix, you should be able to know this is row 5 and column 4 in the matrix. Identify the type of common matrices. We're going to look at dense, triangular, diagonal, sparse, upper triangular, lower triangular, tridiagonal, pentadiagonal matrices. Define and calculate matrix sparsity. Define the purpose of a linear solver, like why do we need a linear solver, and define the two approaches for solving linear equations. So those are direct and iterative methods. You probably learned in school a direct method like Gaussian elimination. We're gonna dig a little bit into more details onto what direct solvers do, how that translates into round-off errors, are there gonna be truncation errors or not, etc. We classify linear systems of equations and identify which solution method is more appropriate. Do we do a direct solver on the system or an iterative solver? Hint, hint, for everything you're going to be doing from now until you graduate, you're just going to be a solver. But once you graduate and start working with big data science, you cannot use direct solvers. They become very expensive. You use what's called iterative solvers, and I will teach you about that as well. The things in red here are all optional. Probably this year we're going to cover Jacobi and Gauss-Seidel iterative solvers and implement them together. And I will also teach you about algorithmic complexity, both time and space complexity. So time complexity of an algorithm tells us how much the cost is going to be as we increase the number of equations, for example. Like, does Gaussian elimination cost more than tridiagonal matrix algorithm when the number of equations is 1 million? Okay, and we'll talk about space complexity, which is the storage and how much memory requirements are required per algorithm. All very useful stuff, all right? And we will start doing that next Tuesday, all right? Have a great weekend. See you soon. Let's begin. Welcome again. It's a Tuesday. We're going to start on digging deeper into linear solvers. You remember last time we finished class talking about the first actual unit in numerical methods after error analysis, which was just kind of scratching the surface and helping us get our feet wet with Python. Our first chapter in the first unit, which was solving algebraic equations, is focused on linear equations. All right? The first question, though, is what is a linear equation? Let's see your name tags and participation. What do you think a linear equation is? What's a linear process? What's a linear thing? What does it mean? If you have something that's a linear. Okay, but what does that mean? Okay, but how could you describe it physically, for example? Go ahead, intuitive. Yeah, okay. So let's say, I'm pushing this laptop. Okay, if I put this much force, it's going to move that much. If I double the force, is it going to move twice the distance? Probably, if it's a linear process. Okay, so a linear process is a process where the output is linearly proportional to the input. In other words, let's say that rate of how the input changes as a function, how the output changes as a function of changing the input, that rate is constant. So if you double the input, the output might double. If you quadruple the input, the output will quadruple, right? So that's a linear process. Anything else is nonlinear. Some processes, that rate is dependent on the input itself, right? So a linear equation is one where, this is kind of the technical definition, the unknowns or the variables show up in a linear fashion rather than being squared or acted upon by transcendental functions. Okay? For example, when you're looking here, if x is my unknown, it shows up linearly in the equation. It's not being squared, function, etc. Same here. A, y, and c, you can call all of those variables, but if a and c are chosen as parameters as values, fixed values, and y is the only dependent variable that depends on everything else, then y shows up linearly here. In this equation, our unknown is u, and u shows up linearly here. It's not squared, it's not under square root, sine, cosine, logarithm, etc. Okay, so let's look at these equations, which we will call nonlinear, which is nonlinear. X is the unknown in this equation. It's under a square. So if you change x, x squared is gonna square that input. Okay, so that's how you think about it. Square root of y is nonlinear in y, because if you double y, square root of y is not gonna double anything different. Okay, so that's what we mean by nonlinear. Log u, if you double u, log u can double. Okay, so it's not a linear process. All right. Now, one thing you should note, and as we go through the lectures and see more equations, we're going to see equations where we have multiple unknowns, or we're going to change the meaning of what we're looking for. So the correct way of saying something is say, this equation is linear in y. So I have y c of we get to nonlinear equations and later on polynomial data fitting. Okay. All right. Of interest to us here are systems of nonlinear equations because I know you know how to solve a linear equation 4x equals 3. You know that x equals 3 over 4 does the issue. We wanna deal with systems of linear equations. When you have many linear equations that are connected to each other, and typically you want as many equations as there are unknowns. Let's say you're tracking temperature and pressure in a system. One equation for the temperature and pressure to solve and temperature, you need two equations to be able to solve for pressure and temperature. Two unknowns, you need two equations. Three unknowns, you need three equations. So whatever system you're dealing with, you need to have as many equations as there are unknowns. The unknowns, typically we use x, y, z, variables u, w, etc. These equations, if you remember the fire dynamic simulator, the example I showed you, where they had these big simulations of the airflow and temperature, it had an unknown temperature, velocity in three directions, z velocity, energy, all that's related to temperature, concentration, etc. As many unknowns as there are points in that computational domain, you need one equation for each unknown. As many equations as there are unknowns. And typically these equations, they tie into each other. So in engineering, with linear equations, for data analysis, believe it or not, and solving problems, it's all about solving systems. Okay, so they are inescapable. Linear algebra, mathematics. One of the very important concepts in chemical engineering, and that you're kind of starting to learn about more, concept of conservation of mass. I introduce it here because it allows us to start building problems together, solving problems together, to result in systems of linear equations, so that you can solve them. So then I can give you a problem. Mass balance. Sure that equation, so it gives it more, a little bit better insight into it than just the math problem itself. All right, so typically, conservation always results in a system of linear equations, and you will study that. I will introduce it to you here. If you consider a system where think of it as think of this as a bucket. You have, or the like the water, the gardener, what do you call it, the thing, water from, there's water coming out from this bucket, okay, and then you're pouring water into it. I know the arroz water in can, whatever it's called. So you're putting in water, phenomenon. Backyard went up. Water comes out, then there's water. But there's a balance there. Whatever is left inside the bucket, whatever is coming minus, right? Kilograms per second, 3 liters per second, okay, and then 2 liters leave, then you have 1 liter. Left and inputs minus output. Now, as we say, when is we say that activation is 0. Okay? Whatever is coming in. So, as you know, so there's like this, or if one person comes in, one person leaves, right? When you're picking so you have a complete balance, and that says inputs equal output. So what I'm showing here is a simple diagram of you're mixing pizza dough, olive oil, and liquid. Other liquid, right? And these which are the mass per second, or volumetric flow rates, liters per second, and given concentration, C1, and producing some other liquid, the mixing and the reaction, the different concentration, C3. So we're bringing in two liquids at flow rate, and we're producing a liquid at a flow rate, at a rate of Q3, so kilograms per second or liters per second, and a concentration C3. Okay. Typically, this balance would be expressed very simply as Q1 plus C2 Q2 equal to C3 Q3. Very simply, right? So if you know the flow rates, in this case, meters cubed per second, kilograms per second. So very simple. Concentration, flow rate. This is process engineering. And we're asking that we know the following. In bucket 1, we have concentration C1 in bucket 1. And what's coming into bucket 1 is Q1 at 5 cubic meters per second and some initial concentration of 10. And then Q4, and then it just kind of goes through the system. Sorry, goes to Q3, which is 3 cubic meter, goes into bucket 3 with a concentration of C3. And then we know the flow rates, Q2, Q5, Q2, Q6, and Q4 over here. Those are all flow rates. And the question is, find C1, C2, and C3. Okay, the question is find C1 and C2. Okay, so what do we know is all the flow rates everywhere. And we know for a fact that C is coming. So for example, we can apply a simple mass balance. To bucket 1 must be leaving bucket 1. So think about it this way. For bucket 1, we have times plus C2 times Q4 equals C2 times Q3. here, which is bringing C2, and it's all leaving to dump into C1, right? So coming in C1, Q3. Now when I solve them, I know I have three unknowns, C1, C2, and C3. And therefore, I need three unknowns. The C1, C2, and C3. We're going to use mass balance that. So let's try to do bucket 2. What do you think the balance of bucket 2 is? Bucket 2. Whatever is coming in equal whatever is leaving. So for bucket 2, what's coming in is Q4. And 3 Q1 times Q5. So input you get first on this the train while the car is ride out. All right, so like that. This is going to be late, but what I want to show here is try to elevate just our thinking a little bit further and abstract thing way that we can communicate more generally about linear systems of equations. So what I will do, I will rearrange this and put all the unknowns on the left-hand side and put all the known values on the right-hand side, okay? So on the first equation, I know C1, C2 are the unknowns. What I know is 50. I put it on the right-hand side. For equation 2, I have 4.5 C2 minus 1.3 C3 is 0. And finally, for the last equation, minus 3 C1 plus 3.3 C3 equals 0. OK, that's great. All right. So let's continue elevating this. This is all good. And you've seen this. We can try to do it by hand or put it in a matrix form, whatever. That's not the point here. I want to lead you to wanting to write it in matrix form. So now notice I aligned all the unknowns by their order, C1, C3. Now when you look at this, C3 is from equation 1. It's equation 1, but it has a coefficient of 3. So equation 1, C1 minus 1.5 C2, 0. Equation 2 is missing C1. So it's like 0, 0 C1, 4.5 C2 minus 1.3. So if you do that, then you can write this system in this transition form where I coefficients, column vectors, okay, multiply them by the unknowns. And there's a reason why I'm doing this. To recover the original equations, this would be 1 plus minus 1.5 C2 plus 0 C3 equal 50. That's indeed my first equation. 3 C1 minus 1.5 C2 plus 0 C3 equal to 50. Good. Equation 2 is 0 C1, so no C1, plus 4.5 C2 minus 1.3 C3 equals 0, right? So I'm doing this row by row, all right? Okay. So that's the transitory step, like, this is cool and simpler than writing 3 equations. I just have to write these column vectors and write these unknowns one time, right? But then there's an even easier way of writing this. If you combine all of those, if you were to combine all of those together, then these unknowns in a column vector and use this to write this system of equations, as a matrix vector product equal to the right-hand side. That's why I moved all the unknowns to the left-hand side. Now, you should be able to see that the product of this matrix with this column vector of unknowns, you recover the original equations, right? So for the first equation, this is equation 1. 3 times C1 minus 1.5 C2 plus 0 C3 equal 50. You should be able to know this. You did very well on exam 0, so I'm not going to go over that. But what I like about this is that it's cleaner, it looks better, it looks more beautiful than just a bunch of equations. All the things, right? I can see all the unknowns in all the equations, even if they have the same coefficient. Okay? But I can also reason about. Turns out that this matrix is what's really important in this system, not the right-hand side, this coefficient matrix as we will. About a matrix, this is our time to introduce a matrix to you. And you've seen matrices, you're learning about matrices now. Tip 1, always connect, a matrix doesn't come out of the blue. A matrix is 100% of the time connected to a system of linear equations. So you see what system of equations does this represent? It represents a system of linear equations. The matrix only giving you the coefficients. But what are the unknowns? What are you trying to solve? Second tip is each row in the matrix corresponds to one of the equations. Row 1 corresponds to equation 1. Row 2 corresponds to equation 2. Row 3 corresponds to equation 3. How I like to think about it. Okay. The columns just give you the different coefficients across the equations. Okay. So now we will call this coefficient matrix A. The nomenclature I will use in this class is either boldface A or boldface A within brackets. I will use those interchangeably. And then we call this guy the column vector of the unknowns as the solution vector. Call it X because we always use X as designating our unknowns, although it's C here, contains variable C. It doesn't matter. I don't care. And then the right-hand side, we typically always call it B. Okay? So now, we started with 3 equations, etc. We can write the whole thing as AX equal B. You've seen this, right? You're seeing it right now. Okay? It's good to see it again and think about it in a different way. Okay, so our objective now is to find X. See where we started? We started with like specific numbers, etc. But I don't care about those. What I care about now is finding the unknowns. But finding the unknowns, I need to know the system. Turns out I need to know A. Okay, so how do we find X? Here's an interesting analogy that I know you know talking about Gaussian elimination and whatever. But bear with me for a second, and I hope this would be an interesting aha moment for you. So here's an analogy with a single equation. If you had AX equal B as a single scalar equation, 3x equal 5, right? You'd say X is B over A, or 5 over 3, or whatever, 1 over 2, right? Okay. So why not do the same analogy with this system of equations? Why can't we say X equal B over A? This will actually lead you to why we call it the inverse. That's what we're trying to do. We're trying to find X equal B over A. Except that, how do you do 1 over a matrix? Is it 1 over each element? Is it 1 over the diagonal elements? I don't know. It's undefined. So technically, 1 over A, this procedure of B over A, so you have 1 over A times B, it's undefined. Like, how do we define that? But technically, that's what we need to do to get X. So it turns out you can divide by a matrix, but instead of calling it division for the matrix, we just call it the inverse. But what is the inverse? It's 1 over something, right? What's the inverse of 3 is 1 over 3. What's the inverse of a matrix? It's like technically 1 over A. It's as if you're dividing by the matrix. So it's the same analogy as a single equation, AX equal B, X equal B over A. Except for a matrix, you don't divide by the matrix. You say we multiply by the inverse. to kind of, make it a little bit, sound a little bit, but technically it's doing B over A, right? It's just the 1 over A for a matrix, or the inverse, has a special meaning. It's not equal to 1 over the elements in the matrix. It's not equal to any of those things. It's a more complicated thing to do. Okay, so we will call this A inverse from now on. And we know that the solution, when you have a system of equations written as AX equal, we know X is A inverse B. So when you do this process, and you can verify that this is a consistent process. Matrix is a two-dimensional entity, right? It's n by n, right? And these x and b, they're vectors, they're column vectors. But you can verify that the product of the matrix by a vector is going to be a vector. N by n times n by 1 is n by 1, which is x, okay? Now, the purpose of linear solvers is to do one of the following. Either find the inverse of A, so we can do this operation and obtain x, because our objective is to get x. So a linear solver will do that for you. Will either find the inverse or find an approximation of the inverse or solve the system without even computing the inverse. Yeah. You're probably only familiar so far with just finding the inverse. Gaussian elimination is a process that finds the inverse and gets you the solution immediately in the process, okay? But it's still finding the inverse. But there are techniques where we don't need to find the inverse, called iterative methods and stuff. So we will learn about those, at least be exposed to them. All right, the brute force approach, the brute force solution, and the method that you're familiar with is called Gaussian elimination. Okay, so Gaussian elimination is called a direct solver. Suspend that thought for later. We will discuss what we mean by direct solvers. But in general, direct solvers, they solve a system of equations exactly. The only errors included in direct solvers are round-off errors. There's no approximation to the matrix. There's no other funny business going on. You solve the system exactly, but you're crunching numbers and multiplying and dividing and subtracting and adding. So you're incurring round-off error on a computer. Okay? Even if you're doing it by hand, if it's not integer stuff, it's gonna end up in round-off errors. Okay, but direct solvers like Gaussian elimination will find that inverse for you exactly. You solve the system exactly, plus round-off errors. Okay? For this, we will use built-in solvers in Python to solve most systems of equations. So I can finish the entire discussion on linear solvers today, teach you how to do it in Python, and we will be done. Okay? However, this is only a small piece of the world of linear solvers, because once you hit on systems that are very large, you're talking 100 million, 10 billion degrees of freedom, 100 billion variables. So we're writing a big proposal right now for the DOE, and one of the problems we're solving, I guess this is recorded, so I'm going to tell the world the problem we're solving. But we're solving a very important problem. And I was just doing an initial cost analysis of how many points I need to solve that problem. 177 billion points. Now, at each point, I have at least 7 unknowns. Let's say 10 unknowns. Okay? So you're getting 1.7 trillion unknowns in total. So that's the scale you are talking about. Direct solvers, as I will show you later, they're good for like maybe 100 equations, or like maybe 200, 500, 1,000. But then in a process where you have to repeat the solution over and over and over again because the conditions change in the system, there's no way we could use direct solvers. Okay, now you might not end up doing the problems that we're solving, but if you end up doing anything that has to do with data science and machine learning and processing data, doing interpolation on big data, regression and stuff, you will end up also with very large systems of equations on the order of hundreds of millions. And you cannot solve those exactly with Gaussian elimination. we have to use other methods. And I will teach you a couple of other methods. But for now, for small systems, 500, even 1,000 equations and 1,000 unknowns, we will just use tools built in Python. I don't want to teach you Gaussian elimination. It's just mundane. You've done it before. It's a mechanistic process. We will just use a tool in Python that will do the job for us. For the most part, this is sufficient. Unless you're doing some advanced research stuff, using built-in tools in Python, I cannot stress that enough, is going to be sufficient for you. All right. So let me introduce you now to the concept of Pythonification. I came up with that a few years ago, and so let's see the definition. It's the conversion of a mathematical formula or abstract concept into code using the Python programming language. Actually, the students made a T-shirt about that last year, so it's pretty hilarious. So for example, Professor Saad asked us to Pythonify a system of linear equations, okay? Or also, Pythonification is the interpretation of everything in life through a Python lens. So for example, when sitting at the table, Josh said, from kitchen, import dishes for dish in dishes. When his mom interrupted, will you stop Pythonifying our dinner, please? So don't Pythonify things in life. If you're like me, use Python a lot. Everything becomes in Python. And so I was teaching my son the other day about algorithm and explaining to him kind of a sequence of steps and how I use that in my work. Anyway, so we're going to Pythonify a system of equations now. In other words, you're presented with a system of equations. I'm also offended that nobody laughed at this joke. So maybe if you can help me make it funnier for next year, that'd be great. We're going to Pythonify the system of equations. In other words, when you are given a system of equations, how do you solve that in Python? That's the question we're asking right now. Okay. However that system is given to you, you will probably derive it by hand, deduce it by hand from doing a mass balance or some force balance or something, and then you put it in Python. Here we're going to focus on how we put it in Python. There are two popular routines that we will use to solve systems of linear equations. And the first one is from NumPy, our friendly module for numerical Python, numerical computing. It's from the NumPy library, from the linear algebra submodule called linalg, and it's called solve. So numpy.linalgebra.solve gives you the routine that solves a system of equations of the form ax equal b. What do you need to give it? You only need to give it a, which is this coefficient matrix, and b, which is the right-hand side. So internally, what this does, it goes and does Gaussian elimination and gives you the solution directly. So this will result in the solution directly, but it's doing Gaussian elimination internally. So this is the coefficient matrix, and this would be the right-hand side vector. Okay. Before I show you how we build the matrices, suppose that you build, so you import from numpy.linalgebra, you can just directly import solve. And suppose we know how to do the matrix A, how to do the vector B. You say x, my solution, is equal solve A, comma B. So it's going to take the system, the coefficient matrix, the right-hand side, and give you the solution, and you print out the solution or do something with it. The other popular routine is to go after the inverse directly. And also from numpy.linalgebra, you have the inv routine or inverse, and then you give it A, and that computes the inverse. Okay? But then you still need to do one more step. So you need to take the inverse of A, call it A inverse, and then you need to multiply A inverse with the right-hand side to get the solution. Remember, our solution was A inverse B. Okay, how do you do matrix vector multiplication in Python? The simplest way is to use the @ symbol, the one you use in your email. So matrix A inverse at B gives you a matrix vector product. What's nice about this is A inverse and B and X, you don't have to worry about them being row or column vectors. Python is smart enough to figure that out for you. So the way we're going to input the right-hand side is just going to be a sequence of numbers separated by a comma in a NumPy array. You don't have to tell it this is a column vector or a row vector. It will figure that out on its own. Okay? Well, this is what's great about this approach. Okay. So how do we build the coefficient matrix and the right-hand side vector? For small systems, you just input things by hand. using nested lists. For larger systems, it's a different story that we will discuss later. But for now, for small systems like this one, it's a 3 by 3, right? You can just input these as a list in a NumPy array. So don't use numpy.matrix or whatever that is gonna get you on a wild goose chase. So don't do that. Just use the method I'm presenting here. Very simply, create A as a nested list. So in other words, as a list of lists. Remember, lists are Python stuff separated by a comma with square brackets. So I open the outer bracket, which is this one, and then each row, I put it in its own list. What's nice about this, it looks like the matrix, right? It's 3 minus 1.50, 3 minus 1.0, 4.5 minus 1.3, and so on. And B is also a list. Don't worry if this is going to be a column vector or a row vector. It doesn't matter. NumPy will figure that out for you. Okay? All right. So for this problem, this is how we would do it. From numpy.linalgebra import solve, you create A as a nested list, and you create B and pass it to solve as A comma B, and then it gives you the result. All right? So let's go ahead and do that in Python. Get your Jupyter notebooks together, and we'll just copy and paste this so that you get the idea fixated in your head. All right. Let's move this. Okay. And I'm going to move this to crest on. Nope. To move to built-in display. All right. So we're done with this one here. Close and halt. I'm going to create a new notebook together. All right. So our boilerplate really didn't change because you can always call numpy.linalgebra.solve. So if you want, you can do it this way from numpy.linalgebra import solve. But in my opinion, it's just cleaner, just import numpy as np. And just keep that boilerplate, and then call np.linalgebra.solve every time you need it, or np.linalgebra.inverse.inv anytime you need it. All right. So again, I'm not going to document this in detail, but let me just, so fall 2024, linear solvers, coding activity 1. Mass conservation. All right, and so we're going to do it the first way using the solve function, solve routine. Okay, so that would be this first option over here. All right, and I can say A is my coefficient matrix. I open the big brackets, and I'm going to move it to a new line. Okay, so I can put in the rows. The first row is 3. Let's see, 3 minus 1.50, minus 1.5, and 0. And then don't forget a comma after that. And then the second row, again, in its own list. And that second row is 0, 4.5 minus 1.3. So 0, 4.5 minus 1.3. And then comma, and then we go down, and then we put the last row, which is minus 3, 0, and 3.3. Okay, this is the matrix. And that's going to be minus 3, and then 0, and then 3.3. Okay, you can check, compare with the coefficient matrix. Rows, it looks like that. For small systems like this, even 5 by 5, just input it by hand. For larger systems, there will be ways to put it in together. Okay. We will talk about larger systems a little bit later. All right, so now, this is the coefficient matrix. Build the coef matrix. Now notice I didn't put this in a NumPy array. I don't need to. Just keep it as a list. LinAlgebra.solve is going to figure that out on its own. Okay? You don't need to put it in a NumPy array. And then for B, build the right-hand side vector, RHS for right-hand side. And B is equal to 50, 0, 0. Okay? So 50, and then 0, 0. Again, don't worry if it's a row or column vector. NumPy is smart enough to figure that out for you. And finally, solve the system. Saying result is equal, or concentrations in this case, is equal numpy.linalgebra.solve. Okay? Now, if you forgot it, just open the parentheses and press Shift-Tab a couple of times. It gives you the function signature, numpy.linalgebra.solve a comma b, computes the solution, computes the exact solution, x of the well-determined ax equal b. A is a coefficient matrix, and b is the dependent variable values. And if you scroll down, it might have a couple of examples here. Okay? All right. So then I'm going to give it a comma b. And then when in doubt, print the result. Print it out. And this is what you get. OK. You got that? Great. What are these values? OK. In that order. Okay? So the answer, so these are concentrations, and they are put in the order you chose to put the system together. So once you write your coefficient matrix, once you determine, in other words, this ordering C1, C2, C3, that's it. You've locked in the order of your solution. You could order them C3, C2, C1. You just change the equation order. But then the result is going to be C3, C2, C1. So that order of the unknowns is very important. You could do it C2, C1, C3, okay, whatever. Right? But that order is important, and that's the answer. That's the order in the answer that you're going to obtain. Okay? All right. So now let's use the inverse. Using the inverse routine. All right, so now we already have A programmed, A put in, right? So we're going to do A inverse, call it A inv, is numpy.linalgebra.inv. Again, if you're confused, just put Shift-Tab and it gives you the explanation, computes the inverse of a matrix. That's it. I'm going to give it A. All right. And let's see what's in A inverse. Print A inverse. Oh, it's got a bunch of numbers. A inverse should be of the same size as A. For each entry, there's going to be some entry that make together can allow you to do the matrix division. Now, if you take this A inverse and multiply it by B, so A inverse at B, that should give you the result. Okay, and indeed, A inverse convoluted or multiplied by B gives you the same answer as we got before. It's better, right? Because it's really the same thing. It's doing the same exact thing. And it's an exact method. The only errors are round-off errors. They're going to be the same round-off errors. So 19.18 and, and same thing as 19.18, 5.04, and 17.4, right? Same thing as above. It's the same exact procedure. Why would you prefer this one over the other? Sometimes it happens that the coefficient matrix remains the same while you change other things in the system. So let's say you're changing the right-hand side in this system, but the coefficient matrix is always the same. And you're changing the right-hand side 1,000,000 times. You solve for A inverse once, and to get the solution for all the other ones, you just do A inverse times B1, A inverse times the second system, times the third system, and so on. Okay, so you compute A inverse once, and you reuse it every time. Right? That's the advantage of A inverse, of the A inverse method. All right. Window over here. Okay. All right, so now here's the math or mess. In general, suddenly the complexity exploded, okay? In general, a system of linear equations is written in this form. Let's start with equation 1. It's coefficient 1, call it A11, because it's equation 1, coefficient 1, times x1, which is the first unknown, plus A12, which is the second coefficient of equation 1. So A1, that's equation 1. 2 is the second coefficient times x2. And so on all the way to A1n, that's the nth coefficient in equation 1, times xn equals some right-hand side value. And then a second equation, A21, that's equation 2, first coefficient, A21, right? And then A22, that's the second coefficient in the second equation, and so on, a bunch of equations that generally have a pattern in them, Aij, or some value within indices, some coefficient times an unknown equal a right-hand side. Now, you do the same thing we did before. You can translate this into a matrix form, a coefficient matrix that only contains the coefficients. Now see, like just moving from this to that made it a little bit cleaner, just looking at the A's as the coefficients, first equation, second equation, and so on, all the way to an mth equation. The unknowns are in the column and the right-hand side. This is a general way of thinking about systems of equations. And again, if you think about this, the first row is equation 1, the second row is equation 2, and so on. And notice the index, the first index on the coefficient, corresponds to the equation number. So all the coefficients on equation 1, they start with A1 in the subscript, right? All the coefficients in equation 2, they have A2 in the first subscript. Okay. Now, the entries in the matrix are referred to as Aij in general. I refers to the row, and J refers to the column. So if I give you A35, this is going to be in the third row in the fifth column. What that means, this is the third equation that's multiplying the fifth variable. That's all that means. But that's always confusing. Like Aij, A56, is that row or column first? I always got confused with that. Like maybe today I'm finally getting it. But what I always personally used is the word arc, ARC. The first index is row, the second index is column, right? ARC, arc. If you want to use Aij, great, be my guest. If it doesn't confuse you, it confuses me. I like to use ARC to know that the first index under A is the row number, and the second index is the column number. So if I tell you what's A95, then you can tell this is row 9, column 5, ARC, arc, okay? Now here's my question to you. This is a matrix that has m rows, m, and n columns, okay? M rows and n columns. You see that the first index goes from 1 to m, and the second index goes from 1 to n. All right, so to be well posed, what should the relation be between m and n, or the number of columns and the number of rows? Yeah? Okay, why? Okay, well, this can multiply. This still multiplies. This is m by n times n by 1, right? So they will multiply. Mm-hmm.
Is it because when you're taking it inverse, it must be a square matrix?
Okay, but why does it have to be a square matrix? What's so special about a square matrix?
Finding the inverse to kind of go through a process. If it's not a square matrix, it's impossible to get the inverse.
What's so special about a square matrix? Okay, so what does m represent? Yes.
Because you're able to calculate the determinant of the matrix?
All of those are like secondary, right, benefits from a square matrix. But what's intuitively, why do we need m equals to n? So m, what does it represent? The number of?
So that same number of variables and equations.
Correct, yeah. So when we say m equal n, what does m represent? M is the number of equations, right? It's the rows, right? Row 1 is equation 1, row 2, equation 2. You have m equations. And n, you go column-wise, is the number of unknowns that you have. When m equal n, you have the same number of equations as there are unknowns. And I remember I started saying that you have to have the same number of equations as unknowns to be able to solve the system. Otherwise, it's either under or over-determined, right? So m equals to n, that gives you a square matrix, which makes it solvable. If it's not a square matrix, you have more equations than unknowns or more unknowns than equations, you can't solve the system. That's why you cannot find an A inverse. That's why you cannot find a determinant, right? So the reason that you can find an inverse and a determinant is that you have enough equations as that are unknowns. But still, you're not guaranteed to find an inverse, but that's not a problem to worry about. Okay. So yeah, to be well posed, the matrix needs to be square, or the number of equations needs to be equal to the number of unknowns. And then that makes our number of rows equal to our number of columns. And I no longer have m, so I'm calling those n. Okay, go from A1 to AN and A1 to AN in the column direction. Okay. Now, what's beautiful about the matrix representation, it's funny where we started. We started with like these three little equations that we're writing them. Then we wrote them in this transitory form. Then we wrote them into a matrix. We went to NumPy. We built the matrix. And now we're like square matrices, right? So we just in this lecture, we went so far to see a full matrix. And all I'm talking about is matrices. Because that's what matters in linear systems, is just the coefficient matrix. And that's why using a matrix formulation or a representation of systems of equations allows you to communicate generally about systems of equations, because all you care about are the properties of the matrix. Matrices come in all different flavors. Here are a few examples of typical matrices you will encounter. A full matrix, a full dense matrix, all coefficients are there. None of them are zero, necessarily some are zero. An upper triangular matrix where the main diagonal plus all the upper entries are generally non-zero, but everything below the diagonal is zero. So we call that upper triangular. Looks in triangle, right? Triangle on the upper side. Same thing for a lower triangular matrix. So the missing entries are zeros, okay? What's in white up there, the missing entries are all zero. A diagonal matrix only has the main diagonal in it. Everything else is zero. The identity matrix, which you know. Or a banded matrix. This is a very interesting matrix for chemical engineering. Well, you have only a few diagonals that are non-zero. This is specifically called a tridiagonal matrix, but you might have this, maybe one here and one over there. Those show up in heat transfer and mass transfer problems. And in computational fluid dynamics, a lot they show up. We will actually solve a heat transfer problem together in class to see how these matrices show up. Okay, we're done really with just how to solve a system of equations in Python. You know, this is good, this is great. Learn this, don't forget it. Most of the time you're dealing with a few equations, put them the way we did in class, and move on with your life. Okay? But there's more. I say, move on with your life. Okay. So many cases in engineering, however, they result in very large systems of equations. And those are with data science, with computational fluid dynamics, with heat transfer, mass transfer, big, large-scale problems. Okay? Climate change problems, simulation, atmospheric stuff. Excuse me, they all will result in very large systems of equations. In those cases, using a direct solver is very expensive and inefficient. Okay, so here's they become very inefficient. I kind of want to explain that to you, but it's hard to explain why without showing you the data. But the idea is, in these problems, you not only have a system that's 100 million by 100 million. Okay, so remember, if you have a problem where you have 100 million unknowns, your coefficient matrix, the size of it is 100 million by 100 million. Okay, so it's a very, very large size matrix. But not only do you have to solve that once, you have to solve it repeatedly. Why? Because these systems, they evolve in time. And in every instance in time, you have that same system that you need to solve over and over and over again. Okay? So they become very expensive and inefficient. In fact, we will do a problem together later where we're going to try to make a system very, very large and try to find the inverse in Python, and your computers are just going to crash. Right? Just our little laptops are going to crash. Okay. Now here's an example of how a large system of equations could arise, and it's coming from heat transfer. So we're going to consider, again, I don't expect you to know heat transfer. I don't expect you to derive the equation of heat transfer. I will give you these equations. Next year, you will take the heat transfer course, and you're going to be like, okay, great, I'm glad we learned to do this in numerical methods first, because now I can focus on the physics and understanding the heat transfer. But know that, you know, this is real, and this is a realistic problem, and you know, logically, you can understand what's happening in that problem. So we're going to consider heat transfer in some material, all right? So think of this as, I don't know, this wall, okay? So this wall here is exposed to a temperature on the inside and a temperature on the outside. There's some material in it, and that temperature is going to move through the wall and affect the other side, and the other side is going to affect this side, right? Until there's a balance eventually. So if I were to look at this material, like take a slice into the drywall and look inside it, it would look like this. Assume this is the inside of our classroom, and this is on the other side, okay? Some length L. And let's say, just for the sake of the argument here, that you have a fixed temperature. You're fixing the temperature on the inside, and you're fixing it on the outside. It's not unrealistic, because this wall has been exposed to the air conditioning all day. It's probably reached that temperature that the air is at. Same thing on the outside. And there's some temperature change throughout the wall. Or like in your house, okay? The inside wall is probably at 78. The outside wall is like 112, like where I live. And so, you know, there's two different temperatures, and there's something going on inside the wall. The temperature doesn't just go from 112 to 78, right? It has to gradually decline. So this problem is asking what's happening in the wall for the temperature, all right? So now suppose also that you have maybe some electrical wire, or like, you know, your kid just wants to see what happens in the wall if they, you know, heat up the wire or get a, you know, blow dryer and then try to heat it. Okay, so assume that there is some heating going on in that material. Another example would be, let's say you're grilling. One edge of your spatula or whatever, the fork, is on the outside, and the other is touching the metal on the grill, and there's some heating going on, right? There's a fixed temperature, there's some heating going on. The point is that the simplest model or way to describe this problem is by this equation. It's a very basic heat transfer equation. What this is saying is that the second derivative, or the rate of change of temperature, okay, the second derivative of temperature, as it changes along x, along this direction, so it's going from T1 or T left all the way to T right, and it's being exposed to some source heating on the right-hand side. So it's being that temperature is being forced to change, not only by the boundaries, but particularly by this heating source, okay? You will study where this equation comes from and why it looks like this. Okay, and why we do it this way. At the end of the semester, I will explain why we work with derivatives and why it's superior to work with derivatives rather than just algebraic equations. But this second derivative for the temperature comes from what's called the heat flux. What this is saying is that the heat flux in this wall here is balanced by the heat source. And the flux of heat just happens to be related to the second derivative of temperature, okay? Fourier's law. That's what's called. You'll learn this, don't worry. You don't even have to deal with this equation in this class. But I'm going to show you how we can take this equation and tie it into linear systems of equations, okay? Okay, so typically at steady state, like I said, the equation governing the temperature variation is given by this equation. We are after T. We are after the temperature everywhere along the rod. If you're taking ODEs or you're already taking it, you might be inclined to solve this analytically. We're not going to do that here. We're going to solve this numerically. But you know everything else except T. So you know the size of this domain. You know the heat source, this S of X, what it looks like. You know what K means. It's just some number, some coefficient. It's the property of the material. All right. So to solve this problem, what we will do eventually, and we will do this in a couple of lectures, maybe next lecture, maybe today, I don't know. What we will do, put points along the rod. Right? So remember that FDS simulation for the fire, we're doing the same thing here, except we're doing it in one dimension, only along the rod. Okay? It gets very complicated, we do it in 2D, so we're just going to do it in 1D along the rod. How many points do we put here? N points. Could be 10, 100, a million. If I put 1,000,000 points, I'm going to need what? 1,000,000 equations. If I put 10 points, I'm going to need 10 equations. Okay? But those equations are going to be derived from that big equation up there. And together, eventually, we will see that those equations, they look like this. They are a system of linear equations, thankfully, in the temperature. So now the unknowns, those T's, they show up as unknowns. And we can solve for them by solving the system of equations. And I wrote it in matrix form because now you know how to do things in matrix form. And not only that, this matrix is a banded matrix, like the example of matrices I showed you above earlier. And you will see in heat transfer and mass transfer, this is the equation you will always get. This is the matrix that you will always get. So then people will study banded matrices to understand their properties, etc. Okay. So that's just an example of large systems of equations. We're going to do it in the coming lectures. I promise you that. But then that matrix, the size of this matrix, what is the size of this matrix, actually? That's a good question. If I have n points for the temperature, n could be 10, 100, 1,000,000, 7 billion. If I have n temperature points, what is the size of this matrix? And remember, at each point, I need to have one equation.
Is it n by n size?
Yeah. Yeah. Because you need to have as many equations as there are unknowns. So if you put 100 points, you're going to have 100 by 100. If you put 1,000,000 points, you're going to have 1,000,000 by 1,000,000. And trust me, we're going to solve this problem and plot the temperature and see how it changes. Okay. So now suppose you were to do this problem with Gaussian elimination. Okay? So I'm solving this equation in 1D. Right? The cost of, what I'm plotting here is the cost of solving this equation as a function of the number of points. Okay? So I'm putting 10 points, 100 points, 1,000 points, 1,000,000 points, and so on. And just measuring the cost of using Gaussian elimination or the built-in tools in Python. Forget the black curve over here. Focus on the red and the blue curves. Okay? So on the y-axis, you have time to solution in seconds. So 10 to the minus 4 seconds, 10 to the minus 2, 0.1, 1 second, 10 seconds, and so on, as a function of the number of equations or the number of points. So this is 10 points, 100 points, 1,000 points, 10,000 points, and look at the cost. This is a log-log plot. If you go to a linear plot, this is exponential. So for 10,000 points only, the cost is 10 seconds. Now you might say, oh, it's nothing, Professor Saad, 10 seconds. But if you were to do this over and over again because you're studying the change in time, and you want to do this over 10 billion times, you just cost 100 billion seconds, your cost is. It's inconceivable. It's ridiculous. What I want this to be at is 10 to the minus 6, actually. That's what I want it to be at. Okay? So that's the cost of Gaussian elimination as you scale the number of equations or the matrix size. The matrix is tied in directly to the number of equations. N equations, you have n by n matrix. The larger the matrix, the more costly Gaussian elimination is, and it's not a straight line, it's exponential. The cost rises exponentially. Okay. So now it gets worse in 2 dimensions. This is the heat equation in 2 dimensions. You get what's called the Laplacian. Don't worry about that. It's a 2 derivatives, 2 second derivatives, one in the x, one in the y direction. So only in 2 dimensions. So this is a plate. You're heating your stovetop, okay? And there's like heat coming on the pan, and it's being distributed, okay? Look what happens. Look at this blue line. Only 60 equations, okay? 60 equations, and my computer crashed. 60 equations in each direction. So, or 60 points. So the plate, you have 60 by 60 points, and so, and the cost of Gaussian elimination crashed. There are advanced solvers like this red one called algebraic multigrid, very fancy solver. The cost remains the same. Okay? You're not going to learn about that. You can take my graduate course and I'll teach you about this. But the point is here, direct solvers for large systems of equations is a bad idea, period. So only use NumPy and algebra solve and inv for relatively small systems. Okay? And then you'll be fine. Okay. So let me talk a little bit about computational complexity, which is a topic I introduced for the first time last year. You've heard of the word complexity. People throw it around. There's time complexity, space complexity, algorithmic complexity. You've seen sometimes maybe like this algorithm is order n. Have you heard that? Or order n log n. Has anyone heard anything like that? No? Yes? No? Okay. So I'll explain that to you very, very briefly here. For an algorithm like Gaussian elimination, we distinguish between, so strictly from a computational science perspective, any algorithm has 2 features. We call them space and time complexity. Okay? Definition, time complexity is the measure of how long an algorithm would take to complete given an input of size n. So think of Gaussian elimination. That's why I plotted the cost of Gaussian elimination versus the number of equations. So how does that cost change as I change n and as I take n to infinity? Well, it was exponential, right? So that's the time complexity of the algorithm. What we would like to have is linear complexity or sublinear complexity. You know, even below a straight line. We want the algorithm cost to remain nearly constant as you change the input size. Okay? Because we are interested in taking our algorithms to very large problems, very large scale. So this is typically measured by counting the number of floating point operations in an algorithm, like how many additions, multiplications, etc. If an algorithm has to scale, it should compute the result with a finite and practical time, even for large values of n. For this reason, complexity is calculated asymptotically as n approaches infinity. So that's why you can't say anything about an algorithm when you do it for 100 equations. Yes?
So would the complexities be the same as the number of rows or
Pardon me?
So would it be the same as the number of
So it's for the Gaussian elimination. Yeah, I think it's n cubed or something. Yeah, so it doesn't scale well. It exponentially grows, polynomially grows with n. What you want it to grow linearly or sublinear you want. I'll show you a plot in a second, a curve where distinguish the two. And then we have space complexity, which simply refers to an algorithm's memory requirements only. Okay? So we will touch on that later. when we look at a matrix that's mostly zeros, for example, only a few non-zero diagonals, okay? You have n by n size, and you're storing everything in it, and mostly everything is zero, you're committing a large portion of memory to store zeros. So why store the zeros, right? There are methods where you only store the non-zeros and figure out where they are located in the matrix, and that's much more efficient. So in general, if you plot the number of operations or the complexity versus the number of inputs, horrible algorithms are superlinear or nonlinear. So this is the straight line. This is an algorithm with linear complexity. The cost scales with the number of equations, for example. All of these here are nonlinear algorithms. The cost increases very, very quickly with number of equations. This is where Gaussian elimination is order n cubed. It's a good point, right? As we increase the number of equations, the cost explodes, okay? What you really want to be is here, like order n or order log n or order 1, even a constant. You want a constant cost, ideally, for your algorithm. So if you see papers, if you're inclined to computer science stuff and like numerical computing, you will see papers telling you, oh, we're going to sort the matrix with an algorithm of order log n. This is what it is. It's just the cost of the algorithm as the number of equations changes. OK, so I'll give you a minute break, and then we'll start digging a little bit under the hood to see what's going on with these systems of equations. OK, there's a lot more to talk about, so we're going to have a few more lectures on this. OK. Hey, Davin.
We just, before we published these, we wanted to make sure that I think the average came out to like an 84.
OK, that's fine.
Is that like, do you have like a goal?
No, I don't. Even if they all get A's, I don't care.
Okay, that's what I wasn't sure if, like,
Yeah.
we were trying to be pretty generous with the first
Yeah,
one.
that's fine. As long as you gave them sufficient comments.
Yeah,
Yeah,
definitely.
yeah,
We just wanted to check with you before we just like sent
Yeah.
them out. We're like,
Yeah, so once you post the grades, send out an announcement like Ainsley and Ariana used to do. Say, hey, good job, everyone. We noticed that you missed this and this. Make sure you get your formatting done correctly, or we will start ducking points next
Okay,
time.
sounds
Makes
good. I
sense?
think
Yeah.
We wrote that on a lot of the comments too. But that's
Yeah, but and tell them, please review the comments we put in, and like if you can have one or two common things that you saw throughout, mention those in the announcement. You know how to do an announcement?
Actually,
You don't?
no.
Yeah. So if you go numerical methods TA, and just announcements.
I just,
Yeah, and just plus. Yep.
okay.
Yep. Make an announcement and say, hey, we just posted the grades. Good job, etc. Common mistakes were this and that. Make sure you read your comments. We will duck points next time, etc. And then, yeah, whatever. Yeah.
Did you post the next homework?
I did not because I'm gonna post it Thursday.
okay.
Yeah.
It's
So.
just, it's gonna be, it'll still be due next week.
Yeah. We missed. We were a little bit behind this year
I wasn't
because.
sure it was gonna be like a today and then due next.
No, it was. Yeah, this year I'm taking it a little slower. Yeah. So.
Cool.
Yeah.
Sounds good.
Anyway,
Thank you.
Thanks, Davin. All right, let's resume, and we'll finish this pretty quickly. So we're going to go under the hood and dig a little deeper into more details of how we solve systems of linear equations. And we'll be reminded of this form AX equal B. In general, we categorize, remember the purpose of linear solvers was to find A inverse, find an approximation of A inverse, or find the solution without computing A inverse. Because that's the purpose of linear solvers. And linear solvers fall under two broad categories: direct methods and iterative methods. Okay? Direct methods, Gaussian elimination is one example of a direct method. It's a general approach to solve an arbitrary system of linear equations. There's nothing specific about the coefficient matrix. Any well-posed system of equations can be attacked with a direct method. They typically focus on finding the inverse or solving for the unknowns directly, like Gaussian elimination. And this approach is exact. The only type of error are round-off errors. Iterative methods, on the other hand, they are very effective and much cheaper for what we call sparse matrices. For now, a sparse matrix is a matrix that has a lot of zeros in it. Only a few non-zero entries. Okay? We will study and define sparsity later. So for sparse matrices, it turns out that like 99.9% of conservation laws like mass, heat, energy, momentum, balance in chemical and mechanical engineering systems, they all result in sparse matrices. Good? Turns out that direct methods are bad for sparse matrices, but iterative methods are really, really good for sparse matrices. And the larger the sparse matrix is, the better and the more efficient the method is, the iterative method. Now, in addition to round-off errors, so they have round-off errors, there is also iteration error. What we call iteration error is essentially that we will never get to the exact solution with iterative methods. So the error there, we call it iteration error. It's like a truncation error because we're never going to get the exact answer because we're approximating things. So that's what we call iteration error. Okay? But they also have round-off errors. Now, the choice of which solver to use, whether direct or indirect, it depends on on the coefficient matrix. That's why the coefficient matrix is so important. So here's a diagram that I put together. If the coefficient matrix is small, then just use a direct solver, like we did in Python. Okay? If the coefficient matrix is large, you have two options. Large and sparse, you can use an iterative solver. Or if you want to use a direct solver, you're like stubborn, I want to use a direct solver on the sparse matrix. There are special direct solvers that are much, much, much faster than Gaussian elimination. They will give you the exact solution, but only work for a few types of sparse large matrices. Okay? Now, if the large matrix is dense, you're kind of doomed. Thankfully, that's not always the case. But in that case, this could occur in big data science. You have to use other special direct solvers like gradient descent methods, which would approximate actually the system of equations and try to find the solution in some fancy, interesting way. I don't think it will never get you the exact solution, but it's one method that works well for dense solvers. In this class, this is what we will learn. We already covered the top portion. Next, we're going to go after large, sparse matrices because they're very relevant to chemical and systems engineering for us. We're going to learn about iterative solvers. We used to cover this, tridiagonal systems, tridiagonal methods, but we're not going to cover it this year. Okay. Direct methods, a summary of direct methods. You have Gaussian elimination. It's a general algorithm to solve arbitrary systems of equations. It's what you learned by hand. There's LU factorization, lower and upper diagonal. If you're taking linear algebra, lower and upper triangle. If you're taking linear algebra, you're probably learning about these things. We're not going to touch on them. We're done with direct solvers. And then there's tridiagonal, pentadiagonal matrix algorithms. So these are special direct solvers for special large sparse matrices that only have 3 non-zero diagonals or 5 non-zero diagonals. Okay? And then you have what we call fast Fourier, fast FFT solver, which is fast Fourier transform. They're efficient for solving periodic problems. Again, this is not relevant here. So, but I just kind of wanted to give you the overview and the complexity of the methods. Iterative solvers, there's a lot of methods with iterative solvers, something from as simple as Jacobi, which we will learn in this class, to methods like Newton-Krylov methods and multigrid methods, which we will not learn. But just to mention them, some libraries in Python contain those. So we will only look at the simplest iterative solvers, and we will use them when we have large sparse matrices, because they're more efficient and they're much, much cheaper than direct solvers. And those, however, iterative solvers, they work for sparse matrices, but the sparse matrix has to be diagonally dominant, which I will define again on Thursday. But essentially, what diagonal dominance means for any equation in the matrix or any row, the main diagonal coefficient needs to be larger than the sum of all the other coefficients in absolute value. That's what's called diagonally dominant. The main diagonal is the values in the main diagonal are larger than the values in the off diagonal, the sum of all of them. Okay, that has importance, physical meaning for that. But there's pretty much for any non-diagonally dominant system, you can rearrange the equations in a way to make it diagonally dominant. So it's not really a big deal, usually. We can use something called pivoting to rearrange the equations. Unfortunately, the lack of diagonal dominance will kill an iterative method. It will not converge. It will become very slow, etc. OK, so we're done with class today. On Thursday, we'll pick it up from here. And we'll start working on building a large system of equations that we will solve together. OK? Thank you. Thank you.